Hello, everyone, and welcome to MRM Highlights. Today's Editor's Pick interview is with Robert Claeser, Markus Zimmermann, and Jon Shah from the Institute of Neuroscience and Medicine at the Jülich Research Centre. Their paper is titled Submillimeter T1 Mapping of Rapidly Relaxing Compartments with Gradient Delay Corrected Spiral TAPIR and Compressed Sensing at 3T. To start us off, I'll now hand it over to Robert, who will give us a brief overview of their work.
Hi, my name is Robert Claeser and I'm going to give you a quick presentation of our work on spiral T1 mapping. Our method is called spiral TAPIR and allows speeding up T1 image acquisition significantly while also improving the fitting accuracy, especially for tissue that exhibits rapid T1 relaxation. You know that quantitative imaging of T1 relaxation may identify structural changes in the brain. To acquire a T1 map, various methods exist that balance accuracy and acquisition time. TAPIR is based on a look-locker readout of a 2D inversion recovery scheme. You can see the sequence diagram on the right side. One of TAPIR's defining features is using multi-slice and multi-line K-space readout after a magnetization preparation module. While reading out 9 lines per excitation pulse allows quick coverage of K-space, it also increases the echo time and the repetition time. This in turn introduces T2 star and off-resonance effects and decreases the effective sampling rate for T1 relaxation over a fixed number of slices per readout block. To overcome this limitation, we wanted to introduce a spiral readout into the TAPIR sequence. Spiral trajectories have high demands on the fidelity of an MRI scanner's gradient system. Delays in the gradient waveform degrade the image quality, but they can be measured and accounted for in image reconstruction. We build upon a delay measuring technique based on the work by Robinson et al., which is shown on the right. The idea of this method is to power one gradient axis at a time with a waveform that is also used for imaging. If the waveform is played out with positive and negative signs consecutively, the time difference of the occurrence of the central peak of K-space can be found by cross-correlating data around the nominal zero crossing. Applying this idea to all of the 28 spiral interleaves we used in our imaging setup yields a good picture of the evolution of gradient delay over the course of a full waveform. Initially we assumed a stationary delay. However, what we observed instead was a transient delay. Consequently, we corrected the observed delay not by a mean value, but using a polynomial correction of third order. Going back to the sequence diagram, we can now see how the readout module is accelerated with the use of a spiral waveform. Compared to Cartesian sampling, TR could be reduced from 24.3 to 14.1 milliseconds and TE reduces from 10.4 to 2.1 milliseconds. Coming to the results, we first had a look at how the gradient delay influences image quality in phantom images. The left part of figure 3 from our publication shows the image reconstruction results without any correction of the gradient delay. In the detail view in the bottom line, ringing and halo artifacts are visible. The central and right part of the figure display the results of the constant polynomial delay correction. Constant correction already improved the image quality significantly, while the transient delay correction, which we developed, reduces image artifacts even further. Of course, we were curious how the reduced TR and TE influenced T1 fitting accuracy. We compared the fitting results of two variants of spiral TAPIR with long and short TR, which we call STS and LTS, with Cartesian TAPIR and spectroscopic measurements. While Cartesian TAPIR shows a mean deviation of minus 2.5% over the voice 229, LTS TAPIR shows a mean deviation of only minus 0.1% over the same voice. STS TAPIR shows a mean deviation of plus 1.6%, which is largely due to the overestimation of T1 for the slower relaxing species. Focusing on the most rapidly relaxing volume of interest, we can see that Cartesian TAPIR is largely unable to capture the signal. LTS TAPIR benefits to some extent from its shorter echo time. STS TAPIR is significantly closer to the ground truth and deviates by only 7.7%. Figure 5 illustrates where the long TR sequences fall short. As the time it takes a long TR sequence to reach the later slices of a group increases, the dynamic range and signal strength of the input values diminish. As a consequence, a proper evaluation of T1 becomes impossible for later slices. Finally, we compared in vivo T1 maps generated from STS TAPIR and Cartesian TAPIR. We found that the maps are highly comparable and that T1 of gray matter was virtually identical. T1 in white matter was found to be about 20 milliseconds shorter when measured with STS TAPIR. This decrease corresponds to findings from other authors who have measured a rapidly relaxing component in white matter, which is commonly attributed to myelin water. Because of its rapid T2 star relaxation, most of its signal contribution has already vanished by the time a multi-line readout reaches the center of K-space. Spiral out trajectories, however, may capture a large part of that signal. We also applied undersampling with compressed sensing by omitting data from every other spiral interleaf. As you can see in figure 6, there is little difference in the appearance of a typical slice as acquired with full Nyquist Cartesian sampling as shown on the left and full spiral sampling as shown in the center. Undersampling by a factor of 2 is shown on the right and again shows only very little difference to full sampling. To conclude, this study developed 2 new methods with application to a T1 mapping. We have shown that the image quality from spiral K-space sampling may be improved with the transient gradient delay correction. Using STS and LTS TAPIR allows generating accurate T1 maps with sub-millimeter in plane resolution. The limitations of Cartesian TAPIR are overcome with the short TE of spiral imaging. Due to the shorter TE and TR, STS TAPIR provides better estimates for faster relaxing T2 and T1 species. This potentially allows rapidly relaxing tissue components such as myelin water to be mapped. Finally, we show that imaging speed can be increased by a factor of 2 to 3.3. Thank you very much for listening.
Maybe to start off, you could tell us about a little bit about your background and how you got into this work.
So my name is Robert. I got into MR imaging via the digital imaging from electrical engineering. I always liked doing digital imaging and got to medical imaging for my diploma thesis. And when I had a look at these images, I realized that compared to conventional imaging using cameras, the image quality is quite poor. And I wondered why that might be the case. So I got interested in the field.
So my background is also electrical engineering, and I also went from digital image processing to medical imaging. And what interested me most is this numerical optimization that we find in compressed sensing applications. And so this was something that really struck me. I was very, very interested in that. And this is how I got into the topic.
So my background is somewhat varied. I started off in low temperature physics in NMR spectroscopy of rare earth alloys at 1 Kelvin, into perspective, and then I moved over from NMR spectroscopy into MRI, did various things, and one of the first labs where I worked at the University of Cambridge, the sort of mantra was that NMR is a quantitative technique, but MRI is not. Let's try to make MRI quantitative as well. And essentially, as you know, the problem is simply time. You can make images quantitative too, but it takes a long time. And so the ideas were born how to take something like a look-locker sequence, turn it into an imaging sequence, and then do not just one slice, but be able to do multi-slice, whole brain, that kind of thing. And we've been doing quantitative imaging for a long time here. And one of the latest pieces of work is this spiral TAPIR.
Is there anything limiting the widespread use of this technique at the moment, or do you think there's more work that needs to be done before it's more widely implemented? Yeah,
for one, we should increase the undersampling factor, because as I mentioned earlier, there's clearly enough room in the signal-to-noise ratio to do that, and also to speed up the image reconstruction process. So the current implementation, as far as I know, is done in Python. So there is some room for improvement with multiprocessing, of course, or getting it to a lower level computationing language. That should help with proliferation.
Do you have any applications in mind to use this technique?
Yeah, for one, dementia research is an interesting topic, because there you really need to have a big study group, a lot of the number of volunteers and also maybe patients. So having an adequate scanning time helps. And if you are scanning people who already suffer from an illness, you might as well keep the scanning time short.
So clearly we're trying to go after the the fast relaxing components, and that implicates myelin water straight away.
Mm-hmm.
And once you are able to look at that effectively, then a lot of neurological diseases come into play. I'm planning a big study on MS patients actually at the moment.
Oh yeah, okay. With I mean, with submillimeter, you can almost start looking at the gray matter. Is that something that you're looking into as well, or mostly white matter?
I think to begin with, white matter, again, the low-hanging fruit, but especially in the MS collaboration, would be very interested in looking at gray matter lesions.
Mm-hmm. Do you have any advice for people that would like to implement this pulse sequences? Are there like challenges that you had to overcome to get this running?
Yeah, so the implementation of the scanning system is, it depends very much on the scanner you're working with. So as it's not a standard sequence, a standard Cartesian sequence, you cannot use a lot of the standard tools that are applied in programming the scanner. So you have to come up with a lot of solutions in the source code actually, and that's the biggest challenge in implementing it in quite some time. So,
Markus or John, do you have anything to add on your end?
I think depending on the scanner manufacturer, it feels a bit like fighting the system when you want to try to implement these non-Cartesian sequences, which is sometimes very challenging, because as a programmer, you might know how you want to implement the sequence, what would be the straightforward way, and then you have to not do it this way, but use it a different way that just works. And that is sometimes feels a bit exhaustive.
Yeah, so having gone from programming these scanners myself to now not programming them, but watching what other people do, I think what's very clear to me is in the old days, the gradient delay correction was a parameter that you had good control over. It affected Cartesian imaging as well, but it was relatively easy to take care of. And over successive generations of programming environments, the manufacturers seem to have hidden these things away from not just the user, but even the idea programmers. Mm-hmm. And I think this method that these two guys came up with is something that's, I think, quite elegant, quite useful, and could actually be applied widely, in particular to non-Cartesian trajectories. You know, with the Cartesian trajectories, and this was the argument right at the start of their work, you have a delay. It's the same delay for every line, and it's really easy to correct, but not with the non-Cartesian trajectories. And so I think this helps a lot for many people who want to do non-Cartesian imaging.
Is there anything else you'd like to share with our viewers about this work or about your broader research interests?
Yeah, so I think for me, the sort of first goals have been achieved. I have this mantra of sub-millimeter, sub-1% accuracy. I think a lot of people in the field of quantitative imaging don't pay too much attention to accuracy and precision. And I'm of the opinion that the whole of quantitative imaging lives and dies by accuracy and precision. And we want to get, we've been working at around a resolution of 1 millimeter for a while, but never really being able to get to that sub-1% accuracy. And one of the thoughts that comes to mind, of course, is that maybe it's partial voluming that is causing these broader distributions. So by going sub-millimeter in resolution, maybe we'll get over that. And that's where we're trying to go, and that's with actually trying to combine a number of correction, if you allow me that term, correction techniques. One is also correcting for motion. So we're looking at navigators that we can build into these sequences to get rid of those line by line shifts, or in this case, trajectory by trajectory shifts, that we can correct those. And I think once we get to something that really is sub-millimeter, sub-1% in a reasonable acquisition time, which I used to define as under 10 minutes. I'm starting to think now maybe under 5 minutes would be better. I think we open up the field quite a bit for really careful analysis of neurological diseases and progression.
Yeah, maybe another point would also be to take into account the not only there's partial volume effects, but also tissue microstructure, which I mean, at some point you can't go lower in resolution, or it becomes more and more difficult. But to resolve it temporarily, and then have a look into the different compartments might be another step towards higher accuracy.
So yeah, to end off, we usually ask people to share with us what they enjoy doing when they're not in the lab, or if there's anything about Jülich that you like to share with the audience if they were there in your city.
Yeah, so when I'm not in the lab, I try to do some karate. I've been on a pause for a while now, but I'm looking to get back into it in 2 weeks. So looking forward to this one.
So running the lab is quite a demanding, time-demanding activity. I tend to travel quite a bit for holidays, and that's normally to one place in Florida. So we enjoy the beach and the sunshine there. And apart from that, I spend my time house building, which is an ongoing project that started some time ago, actually. I don't dare admit how long ago, but that takes up a lot of my time. I actually quite enjoyed it. It's quite therapeutic, building something with your hands rather than with brain power.
Okay. So having used the time, so what I like to do in my free time is I play piano for like more than a decade now. I really enjoy that. And Aachen has some, so I'm living close to Jülich in Aachen, and has some very nice swimming pools, and I like to go for swimming in my free time.
Thank you very much, and speaking to you soon.
Great, thanks for your
All right.
time.
Thank you very much.
Yeah, no problem. See
Bye.
everybody. Have a good day.
Bye.